we are studying the different methods employed in engineering study to validate the design process. When design is embodied, more precisely when the design principles are embodied into a concrete model, we want to make sure that the model works according to our expectations and then move forward. How to check the model and see whether it meets the specifications without contradicting each other is the job of modeling. We have said that there are three basic ways of modeling in engineering. The first one was the mathematical modeling, which we did not analyze in great detail but spent more time in criticizing the model. The point is simply this: why I am not going into the depths of mathematical modeling is mainly because you will spend a lot of time thinking and meditating on mathematical modeling in your future courses. I don't want to summarize everything in one or two paragraphs, it's impossible. Therefore, I try to shed the light on the other aspect of mathematical modeling, and I was giving you a critique of mathematical modeling using Bertrand Russell's paradox. I received a mail from someone without name who was trying to answer the Barber paradox. Though I appreciate the answer given, I want to make very clear that Barber paradox should not be considered as a puzzle. It's not a puzzle to solve, wherein you come up with some witty answer, though you can try such things. I mean, the very simple answer to that question is somebody who is not having a beard, if that person is a barber, the problem will be solved. So if that person is a lady or that person is a child, the problem will be solved. That is not the point. You will miss the point if you try to see the whole issue from that perspective. The issue is something else. The issue is that regardless of how rigorously you try to implement a complete system, there will be some things which are true but you can't prove it. This is what is known as Gödel's first incompleteness theorem. Among the three very important theorems which everybody should be aware about, Gödel's incompleteness theorem, I think, adds a pinch of salt to the whole issue. In the theory of numbers, any system in this world, you try to create as best system as possible, there will be few things inside the system which are true, but you can never prove it. Proving is a method followed in science in general and mathematics in particular to assert the truthness of something. If you prove something, it is true. But what we are claiming here is, it will be true, but you can't prove it. That is the greatness of Kurt Gödel, the genius of Kurt Gödel. Anyway, we will not go into that. So my point was that in any formal system, a complete axioms and theorem set cannot prove everything. So mathematical modeling has its limitation. That was my point. That is why you have to bother about other things. What are the other modeling techniques? We told one of the other modeling techniques is physical modeling. Scale drawings and full-blown prototype models using similar material or using the same material. For example, you have to build an aircraft. Before building the actual aircraft, you have to build a small model. Now when you build the small model, of course you will scale it down. People who have tried their hand in aero modeling will know. We will scale down. The entire aircraft, when you do using aero modeling tools, we are scaling down to the ratio of, what is the ratio of scaling down in aero modeling? Any NCC cadets from air wing background? Well, anyway, in engineering, at least if you are studying carpentry, and after that you may continue with that. Are you studying carpentry in your workshop practice? You are not studying carpentry. Then what do you do in your workshop? Sheet metal and welding and sheet metal. Oh, you are not doing carpentry. Oh, you are missing out a lot of fun. That means carpentry is good. At least we love it. Well, when you scale down, for example, aircraft, there are many questions to answer. For example, an actual aircraft, the construction of wings, let us consider. What will be the material used? Now, can you build an aero model using the same material? And what about the engine? What about the fuel to be used? All these questions, if you try to answer, you will see that, there is no point in building a prototype using a different set of materials from the actual product you want to build. No purpose is served. In software engineering, we call it as throwaway prototypes. You build a prototype and throw it away. There is no use of such prototypes. In fact, the golden rule in prototyping is that you scale down, it's okay, but the materials used and the process used should imitate the actual production. For example, you are interested in studying the aerodynamic character of the wings. What is the use if you build the wings here using plywood? What is the use? The aerodynamic characteristic of that will be drastically different. And finally, try to fly it using your normal flying techniques like a string rubber band, strength of it, and try to fly it. No use of building such aero models. Right? So the point which should be considered in physical modeling is this. Can you use the same material or somewhat similar materials? Similar material in a sense, materials which have same physical, chemical, electromechanical properties. Can you use it? Fine, go ahead. Second, the process of building the actual product and the prototype should be similar. Example again, aero modeling. There is no use if you take a big piece of wood and try to carve out the aircraft. That does not become a model. An actual aircraft will be built by constructing different parts and then assembling together. Can you do the same thing here? If you can, then go ahead. We tell the same principle in robotics whenever we teach students the basics of robotics. The one basic lesson you should learn in robotics is to get rid of this fascination of using all those small kits which are available in the market. Pre-assembled kits. There is no fun in doing robotics using those pre-programmed kits, because then you won't get an idea of how to build the robot from scratch. Such caution should be exercised in all kinds of engineering design while you do the physical modeling. Scaling down is inevitable, but that does not mean that you should substitute materials and processes. One thing I wanted to say. The third technique in modeling is computer simulation. Now here a word of caution. Today if you see, almost anything can be simulated in a computer. You just go and do a Google search, you will know. Starting with road design. If you want to construct a road and you want to decide what types of curves it should have, and if you know how many vehicles pass along that road in an hour, number of vehicles per hour, you can give all these inputs to the system. It will give you a simulation. For 1 hour, for 2 hours, you can see the simulations to decide whether that model is good or not. Have you seen Hebbal flyover? Of course, with all respect, that's a wonderful engineering design. I don't know how many of you know that 99% of the flyovers, underpasses and whatever civic constructions which happen in Bangalore will be designed mostly in MSRIT. There was one professor, Professor Srihari, who is who just retired last semester, who is the main design engineer for almost all this kind of things which happens in Bangalore. So I was, Professor Shear is a very big name in traffic and road security. In fact, once the Hebbar fire happened, anybody who sees it for the first time will be amazed by the complexity of the design. So complex in its design. In fact, it has 4 roads connecting each other, but to make all roads accessible to one another, a fantastic design has been done. But how practical is it? There should be some questions. In fact, if you try to simulate the same flyover which has 8 hairpin curve, 8 kind of curve, twice going each other, intersecting at a point and all that, you will see that the actual speed of the vehicles moving in that flyover will actually be slowered with all those U kind of curves which are there in that flyover. Now those things can be simulated. Many things today can be simulated. There are standard software. You need not write anything. In fact, if you go to industrial engineering, they will tell you that before any production, any kind of production, you can actually simulate and see whether the parameters you have chosen are correct or not. But let me caution that we being software engineers, we should know the truth. There is one famous saying in computers which you may have heard it in your first year. Your teacher may have told you. Garbage in, garbage out. Told. So you should write it in bold letters and keep it in your desk. Garbage in, garbage out. A computer software for anything is as good as how the designer has written the software. What has happened today is people rely on software more than anything. If there is 2 kinds of documents given to a person, there is more probability of a person accepting computer document as more reliable than other things. Computers somehow have become more trustworthier, but the fact remains that it's as good as how it is designed. Why I am saying this is I have seen this peculiar, though it is somewhat related. I will give you this example. I am a practicing astrologer. It has been handed over from generation, so I practice astrology. Anybody is interested? I can do the predictions. It's up to everyone to believe it or disbelieve it. I am not going into the debating tone of astrology and all. Whatever. Why I am taking this point is, today, if you see all around, even in television, even otherwise, people are so dependent on computers or astrology. You see any astrologer on TV, he'll have a laptop. He will key in your date of birth, your time, the place and time, the thing will come. I know that many of the astrological software, of course, in astrology, great amount of things are reserved for mathematics. It's completely mathematical calculations. And computers can do it better than humans in a very fast rate and all that. You know the characteristics of computer. Computers never get bored, they do things fast and stuff like that. But for a particular combinations, when more in-depth study is required, computers fail. What is the basic drawback of computer? Computers can't think, whereas humans can think. Computer is an absolutely fantastic servant. You tell it to do something, it will do. If you ask it to think and do, it can't. So why I am saying this is, increasingly I am getting references. Though I don't offer services for money and other things, I do it only as a charity to only few trusted people. I am getting reference, especially when the matchmaking happens in horoscopes. 90% of the astrologers blindly try to identify some dosha or other dosha, simply like that. 80% ಹೆಣ್ಮಕ್ಳಿಗೆಲ್ಲ ಕುಜ ದೋಷ. It is not that. Anybody who has at least a preliminary knowledge will tell you that it is not a very simple 2-4-7 calculation that you do and say, yeah, you are having this dosha, please do this puja. It's not as simple as that. Certain analysis has to happen which a computer cannot do. Therefore, that on a lighter vein I was saying this, these things happen even in a very serious area like medical image processing. I was recently giving an example of how negligent people are when they design software which can have a huge impact on the lives of people. The color coding of cancer cells. See, increasingly today all the diagnostic tools used in medicine are computer based. What we do is we do color coding. See, if you have a normal cell and a damaged cell, infected cell, how do we distinguish? We do color coding. Infected cells will have some color, this will have some color. Human eyes have a tendency to perceive certain things observed for a long time, even if they are not present. Let me give a very small example. You take a paper, make it into some square kind of a thing, put some black dots, dark black spots in some cells. Watch it for some time and again see it. The perception will be that the cells which do not have that black spot also you feel that there are black spots. Human eyes have some perception value. These things may appear very trivial, but when applied to such complex situations, it is a question of life and death. When doctors are increasingly dependent on computer generated data to take some critical decisions, the problem is magnified. It's happening. There is a very famous case of chemotherapy machine going wrong. It's called as Theorem 25 case. Please go and use Google to find more data about this. This is one important lesson which all of you should know. Theorem 25 computer case. Theorem 25 computers were used to give certain chemotherapy treatment to cancer patients. A very small programming fault. What was the fault? The use of excessive if-else ladder. All of you have used if-else ladder. Do you know that if-else ladder perform very poorly compared to case statements? I don't know whether your teacher has emphasized you on this fact or not. The difference between the timing of completion of these two operations may be very, very small, nanoseconds. But in critical situations, these values are magnified. Many people have died. Who should be responsible? So a harmless if-else statement, if it can cause death of people, we should blame the designer for that. In fact, engineers in India are blessed. Let me tell you, especially we are blessed. There is no code of conduct for us. There is a code of conduct for civil engineers. If a building comes down, a civil engineer who has designed it can be booked. But a software coming down, a software engineer cannot be booked. So we are blessed. But I think it's a shame. Because why we can't be booked? Because there is no accountability, there is no definition. Engineer is not defined in Indian law, first of all. There is no definition of engineer in Indian law, and more so software engineer is not defined. Anybody who has a training in medicine is considered to be a doctor. Such definition doesn't hold good for engineer. No, anybody can become software engineer. That's a problem. Anyway, we will not get into those areas. So my caution was that computer simulations today, I want you to try at least 2 or 3 simulations which are available. Most of it are written in Java applets, so you can use it in your browser only directly. Most of the simulation techniques, the population growth in the world, the effect of somebody was doing in carbon dioxide emissions and all, you can see actually those simulations are done. The growth disparity due to income differences in the world, also simulations are there, you can simulate. In fact, if you have a website and have a list of how many visitors come to your website, you can simulate the network traffic. You can do all that today. But computer simulation is as good as how it is programmed. So unless and until you don't know how to program correctly, the simulation models will fail. What is the basic advantage over computer simulation over static mathematical modeling? What is the basic difference? Mathematical modeling, that is making a mathematical model and simulating it in a computer. The basic difference are two. One is adding an element of randomness. Adding an element of randomness. In computer simulation, it is very easy to introduce a component of randomness. In mathematical model, capturing randomness is tough. Have you written a program to generate random number in your first year? It's a very interesting program. If you have not written, please go and write. Write a program to generate random numbers. Any ideas on how to generate random numbers? Don't use inbuilt function. Come on, it's very simple. For that matter, why do you write bubble sort? Bubble sort is also a standard function. How to generate random number in computer? C program. Well, try. It is a very interesting exercise. You should do it in your first year. Because for me, at least, by the ability to generate a random number, computer becomes God. For me, why computer is God? Because computer can generate a random number. No one can generate a random number. It's very difficult to generate a random number. Random number generation means generating something out of nothing, not following a model. So if you try to write a program which is very methodical, that means you are failing in writing a random number. That randomness should be embedded. Try. It's very interesting. So the difference between mathematical modeling and simulation model is precisely this. Computers can add an element of randomness, one. Second, in simulating events, computer simulations are far better than mathematical modeling. We have to simulate an event which happens between time t0 to t1. Event simulation, computers are always better. Right? There is a separate course in your engineering study which focuses on system simulation and modeling. There you will study more. I don't want to put everything now. So finally, where do we stand now? Now we have seen that starting with concept design to choosing the right alternative among the competing choices, then embodying your abstract concepts into some concrete design, you have evaluated your design by building a model. That is what has happened. After modeling is complete, you are very sure that whatever design you have chosen meets all the specifications, it is correct, it is complete. Now you move forward and try to enhance this design, try to build a more concrete design. That is what I will take up in my next lecture.